Welcome to Unit 3. In this unit, we'll be focusing primarily on chemical reactions and stoichiometry. We begin with the topic of this video, the mole. We already know that the kilogram is the SI unit for mass. The mole represents a similar yet distinct concept. It would be great if we could devote an entire video to moles, the animals with the little pink noses that burrow in the ground, but the mole we're concerned with today represents the amount of substance present. We measure the amount of substance present by looking at how many elementary particles are present. Elementary particles are usually atoms, but they can also be molecules, ions, protons, all sorts of things. A single mole of any substance contains 6.022 times 10 to the 23rd elementary particles. This constant, 6.022 times 10 to the 23rd, is called Avogadro's number, named in honor of the Italian chemist Amedeo Avogadro. It's a fair question to ask why we need the mole unit at all. Why can't we just use regular mass and measure it in kilograms? There are two reasons for this. Firstly, we have to remember that different substances have different densities, so a similar amount of substance will have a different mass. The mole serves as a universal unit that represents 6.022 e to the 23rd elementary particles of any substance. For example, here we have two blocks of metal that are exactly the same size, shape, and volume. The one on the left is copper, the one on the right is aluminum. Despite being the same amount of physical substance, the block on the left has a mass 3 times higher than the block on the right, because the density of copper is 3 times the density of aluminum. In other words, there are more copper atoms packed together in this small block than there are aluminum atoms packed together in this other small block. 1 mole of copper, however, will always contain 6.022 e to the 23rd copper atoms, and 1 mole of aluminum will also always contain 6.022 e to the 23rd aluminum atoms. The second reason is that the kilogram is far too large a unit to use when we talk about atoms or molecules. Atoms are so small that talking about them using the kilogram as a unit leads to absurdly large numbers of atoms. Just to provide one example, 1 kilogram of carbon contains about 5 times 10 to the 25th carbon atoms. That's 5 followed by 25 zeros. It's just not feasible to represent quantities of atoms in a chemical reaction using kilograms or grams. Here's an example problem to help us think a bit deeper about this. Suppose you have 1 mole copper and 1 mole aluminum. Would the masses of these two quantities be the same? Why or why not? The answer, believe it or not, is no. They would not be the same. Yes, they would contain the same number of atoms, that's true. But remember, a single copper atom has more protons and neutrons than a single aluminum atom. So 1 mole of copper is going to have a greater mass than 1 mole of aluminum. The point we're trying to establish here is that kilograms and moles are measuring different things. Mass is a measure of the amount of matter present, whereas moles represent the amount of substance present, as represented by the number of elementary particles. These two concepts are not the same, and it's crucial not to get them mixed up. Amount of matter does not equal amount of substance. That's the point we're trying to clarify here. On a practical level, chemists use moles to represent the amounts of substances involved in a chemical reaction. One concept we'll be seeing a lot of in the coming unit is that of chemical equations. Chemical equations are essentially mathematical representations of chemical reactions. They tell us two things. First, they tell us what chemical substances are involved. In addition to this, they also tell us how much of each substance is involved. This makes them very useful to chemists working in a laboratory. Before I scroll down any further, some viewers might have noticed that I've switched out my red marker for this bright yellow color. I've been told that red isn't the best color to use against this dark background because it's really hard to see at a lower video quality. Hopefully this yellow works a bit better. If it's still a problem, leave a comment and let me know, and I'll either change the color again or change the background entirely. In any case, down here we have an example of a chemical equation. This is a chemical equation for water. On the left-hand side, we have H2 and O2. These two substances react to form H2O, or water, which is written over here on the right. These big numbers before H2 and H2O are coefficients, which tell us how many moles of substance are involved. By the way, the coefficient on O2 is actually 1, but we usually omit writing 1 as a coefficient, just like we do with the subscripts in chemical formulas. So according to this equation here, 2 moles of H2 and 1 mole of O2 are reacting to produce 2 moles of H2Os. We can also represent this in terms of the numbers of molecules being combined. As for Avogadro's number, we can see that we can use that constant to convert between the number of elementary particles and moles, or vice versa. Let's practice that now. Example 2 says, how many moles of water are represented by 30 trillion water molecules? Feel free to pause the video if you'd like to take a shot at this one. Remember, 1 mole of any substance contains 6.022 e to the 23rd elementary particles. So all we have to do here is divide 30 trillion by Avogadro's number, 6.022 e to the 23rd. The answer is about 5 times 10 to the negative 11th power. The unit is moles. As we can see, 30 trillion isn't really that huge a number as far as atoms or molecules are concerned. Another useful concept derived from the mole is molar mass. Molar mass tells us how many grams of a substance are found in 1 mole of that same substance. It accordingly has units of grams per mole. When we're dealing with elements, finding the molar mass is easy. All we have to do is look at the periodic table. The atomic weight listed on the periodic table is equal to the molar mass of the element being considered. For molecules, it's a 2-step process. First, we find the molar masses, or atomic weights, of the constituent atoms on the periodic table and then add them together to find the molar mass of the overall molecule. For this reason, molar mass and molecular weight are usually held to be synonymous. The main practical application of molar mass is to convert from grams to moles, or vice versa, from moles to grams. Example 3 says, calculate the molar mass of water. Use this value to convert the answer from example 2 into grams. Water, as we very well know, has a chemical formula of H2O. If we look at our periodic table, we'll find that hydrogen has a an atomic weight of 1, and oxygen has an atomic weight of 16. These are approximate values. We're choosing to round to the nearest whole number to make the calculations easier. Since there are 2 hydrogen atoms, we calculate 16 plus 1 plus 1 to get 18. This is the molar mass or molecular weight of water. In example 2, our answer was 5 times 10 to the negative 11th, or 5 e to the negative 11th moles. To convert this into grams, we need to multiply it by the molar mass. These two mole units cancel out, and we're left with a final answer of 9 times 10 to the negative 10th, with a unit of grams. Example 4 is similar. Find the molar mass of uranium hexafluoride, it says, and use this value to convert 100 grams of uranium hexafluoride into moles. This problem is bringing together some of what we learned from chemical nomenclature in Unit 2. Uranium hexafluoride has a formula of UF6. According to the periodic table, the atomic weight of uranium is about 238, and the atomic weight of fluorine is about 19. Again, we're rounding to the nearest whole number here. Since there are 6 fluorine atoms, we do 19 times 6 to get 114. The molar mass of the overall molecule, then, is 238 plus 114 equals 352 grams per mole. On to the second part. This time, we're starting with a quantity in grams, so we need to divide 100 grams by 352. The answer is approximately 0.284 moles. Yet another way we can use moles is to use them to determine the chemical formula of an unknown substance. This is a very common type of problem in geology and earth sciences. Let's say a group of miners find 20 grams of a mineral. They can do an analysis on this mineral and find out that of the 20 grams, 14 grams is gold and 6 grams is silver. Using this information and what we're about to learn in a few moments, they can actually determine a chemical formula for this mineral they're looking at. We can even do this if we only know what's often referred to as the percent composition of a metal. For example, if we have a mineral that's 75% copper and 25% tin, or something along those lines, we can use those percents to determine the chemical formula of the mineral. All we would need to do is set the sample size to be 100 grams while we're doing our calculations. Percentages are out of 100, obviously, so this makes everything quite a bit easier. We'll talk about this more in just a little bit, but here are the 3 steps in solving these types of problems. First, we need to convert the masses of the component elements into moles. Of course, if we have the percent compositions instead, we would first find out how many grams of each element would be present in a hypothetical 100-gram sample. Our second step is to divide all the resulting mole values by the lowest mole value. This gives us the molar ratios of each element. Then, if we have any ratios that are not a whole number, we multiply them by a number of our choice to make them whole numbers. Those whole numbers then become the subscripts for our chemical formula. If that didn't make much sense, let's do an example and see if that helps clear it up. Example 5 says, galena is a type of lead ore. A natural sample of galena is found to contain 86.75% lead and 13.25% sulfur. What is the chemical formula for galena? Our first step is to make our lives about 86.75% easier by setting the sample size to 100 grams. From this, we instantly know that of the 100 grams, 86.75 grams are lead, and 13.25 grams are sulfur. Then we convert these to moles. The atomic weight of lead is 207, and the atomic weight of sulfur is 32. 86.75 and 13.25 are in grams, so we divide these by their respective molar masses. For lead, there are one moment here. There are 0.419 moles present, and there are 0.414 moles of sulfur present. The second step is telling us to divide these two values by the lowest value, which is the one for sulfur. 0.414 divided by 0.414 is 1, of course. 0.419 divided by 0.414, on the other hand, is not 1. It's about 1.01. The molar ratio of sulfur to lead in this mineral is 1.01. That's what that number is telling us. Or, if you want to think about it this way, for every 1 mole of sulfur in this mineral, there are 1.01 moles of lead. 1 is a whole number already. We don't need to touch that. The lead ratio of 1.01 is so close to 1 that we can round it to the nearest whole number. This means that the two subscripts are going to be 1. The formula for galena is PBS. Example 6 is a bit more fun, in terms of its presentation anyway. Astronauts visiting an alien planet discover a mineral that they're told has a chemical formula of Ag6Sb3As. The alien floats away before they can ask about its percent composition. Let's see if we can help them out. Our first step is to disregard the floating alien and focus on the chemical formula here. Unlike last time, we're starting with the chemical formula and working our way backwards. We begin by calculating the molar mass of the mineral as a whole. Ag, or silver, has an atomic weight of 108. Sb, or antimony, has an atomic weight of 122. Finally, As, or arsenic, has an atomic weight of 75. If we multiply each of these by their coefficients and add them together, we get a molecular weight or molar mass of about 1087 grams per mole. We'll also be needing the individual molar masses of the elements. The Ag6 term has a molar mass of 648. This means that there are 648 grams of silver in 1 mole of silver. The Sb3 term has a molar mass of 366. The As term has a molar mass of 75. To obtain the percent composition, all we need to do is to divide each of these numbers by the molar mass of the overall compound. This will tell us what percent of the overall molecule is made up of silver, antimony, and arsenic. If we do the calculations, we see that the percentage of silver present is about 59.6%. The percentage of antimony is about 33.7%. Last but not least, the percentage of arsenic present is about 6.9%. It doesn't add up to 100 exactly, because we rounded to the nearest tenth, but if we needed the added precision, we could always add while including more decimals. Before we end for today, I did want to mention that my video notes for all of Unit 2 are available on my website, and I will leave a link to that in the description of this video. In our next video, Unit 3 Video 2, we will talk more about chemical equations. Thank you for watching.